this event is made possible by a number of parties and people, and I want to make sure you know who they are. Number one, it is being sponsored by Confluent and Mosaic Data Science, the Calvin Center for Social Research, and Viston Creative. I encourage you to check them out. There are links to those generous companies on our webpage. I also want to recognize our organizing committee, which consists of David Zeitler, Randall Prime, Michael Bloom, Matthew Morris, Omar Malik, Samantha Milano, David Langlois, Thomas Geib, and Elizabeth Kurth. The purpose of BDI is to build expertise in data science and data-related areas, such as data engineering, IoT, and AI. And we do that by providing content such as this, and also by creating highly connected networks of people like you, experts and ambitious learners from diverse domains and backgrounds. This is important because it's in this way that we succeed personally and that we succeed as a community, that we succeed as businesses and as regions. It's the basis for economic vitality and quality of life. I invite you to join us. So we need people like you, and the people I just mentioned are people like you who have pitched in and worked hard to make this happen and prior events happen and future events. So join us. If you're unwilling to join us, then you are free to donate. You are not required to donate. This is a free event, and it is our pleasure to bring it to you free of charge. If you are so inclined and you appreciate the mission of Big Data Ignite and the content you're receiving here, do feel free to donate. And I think I'm aware that there is a button on our website right now that you can use. So feel free to check that out if you're so inclined. We are broadcasting live via YouTube Live, and we invite you to submit your questions for the speaker by way of Slack. There is also a chat facility on YouTube Live, but I discourage you from using it. Instead, use Slack, because that is where our speaker, Nagdev Amruthnath, will be following up with you post-presentation. So that will facilitate discussion between you and Nagdev and with the organizers as well. With that, I want to quickly introduce Nagdev Amruthnath. Nagdev has spoken in this area before, and most specifically, he's spoken at the West Michigan Ars Users Group. So West Michigan Ars Users Group, who has for a long time been a great content partner with Big Data Ignite. And I'll thank personally Paul Egler for being our closest liaison with the West Michigan Ars Users Group. And Paul is on the call here, in fact, and will maybe make some comments toward the end of the hour. But WMR Users Group, as many of you already know, brings a lot of great educational content about data science with R. And due to the R element of Nagdev's talk, WMR Users Group is co-presenting this with us, and we're happy to have them. With that, let me talk just a bit more about Nagdev Amruthnath. He has an undergraduate. He is the kind of person that I think is extremely effective because of his diverse background. He has an undergraduate degree in information science and engineering, that is to say a CS degree, like many of us have, but he went on to do industrial engineering at a master's level and then at a PhD level. So he's a guy with a lot of training education in both manufacturing processes and also data analytics, and how do I apply computers to solving problems. And the result of this, as I witnessed at his last talk, was a great amount of creativity in applying tools, an enormous amount of tools. I was so excited to hear his last talk because he really introduced a lot of different tools that one can apply in pieces and parts to collect, analyze, and provide insights about industrial engineering. So I also am aware that Nagdev is, from a human standpoint, a guy who is a food connoisseur. He's well-traveled. He's been to many countries. He currently works for Tyson Foods in their data science and analytics department. He previously worked here in Michigan in the Battle Creek area for Denso, a tier 1 automotive manufacturer, doing industrial engineering. And now he's in the area of data science plus industrial engineering at Tyson, also an enormous worldwide manufacturer. So with that, I want to first ask Tuhin Mitra, co-director of Big Data Ignite, if there's anything I've missed. Have I, Tuhin?
Hey, Elliot, thank you for that comprehensive introduction of Nagdev. It's, I think for the benefit of our users, it's really good to hear that. And I don't want to take any more time and jump right into the presentation. I do want our listeners to take a look, if you haven't, in the next sessions as well and plan accordingly. One quick tip for listeners is that this is a good opportunity to have something set up for your lunch and learn sessions, which a lot of office places are doing or communities are doing, especially during lunchtime. So Tuesdays and Thursdays, 12 to 1 p.m. Take it away.
Thank you, Tuhin. Michael or Thomas Skybe, any other comments before we hand it over to Nagdev?
Not really, just welcome everyone, excited for BDI 2020. I'll be monitoring that Slack channel. If you have questions for the speaker, I'll be relaying those to him at appropriate moments from Slack.
So please feel free to contribute questions at any time, and we'll make sure those get to Nagdev as soon as possible. With that, Nagdev, welcome back, let me say, because you've been an attendee at prior Big Data Ignite conferences. We've heard you present, and I'm excited that you're here. Thank you, and go ahead.
Thank you. Hello, everyone. Thanks for attending this session, and thanks, Elliot, for sharing some really kind words. Today, I'll be presenting a talk about hardcore manufacturing and how data science and R is being used to solve one of the most intriguing manufacturing problems, that is the maintenance aspect for it. Today, the focus is going to be on building pipelines using R. So this is a little bit of background about me. I got my engineering undergrad and information science engineering and master's and PhD in industrial engineering from Western Michigan University. And these are some of my social profiles, my LinkedIn and my GitHub and my webpage where I weekly post different data science articles. So feel free to check it out. And these are some of my publications with respect to data science. I'm also a journal reviewer for 3 international journals. I've published a couple of packages, and recently I've been awarded a patent as well. So when we look around us, we are going through, watching this particular stream on a cell phone, tablet, or a laptop, or, place where you're sitting on a table, chair, desk. It actually, all these items went through extensive and complicated supply chains to get manufactured and delivered to you. So every day, all the items you come across, they are all manufactured. And this manufacturing is industry, an intriguing concept that it's very, very hard to understand how all this actually works in a harmony to get to the end customer. And all this just didn't happen like overnight. It actually went through a couple of centuries of process refining, and achieving that best efficiency to get that products to us at the most economical way. So this chart actually talks about how that entire history happened. It started with Industry 1.0, where it was happening between 1700s to early 1800s, where we humans figured out how to use steam energy to run machines. So we started using steam machines to extract oil, to weave looms, and so on. And that's where we also started, we manufactured our first locomotives. And the second industrial revolution did not happen until for the next 100 years, where we started using mass production, where we manufactured everything in assembly lines. And one of the pioneers that we always attribute to is Henry Ford. where he was able to produce that Model T Ford car for an affordable price of $800, where everyone could afford it. And before then, it was something of a rich person's commodity. And after that, it didn't take so long for the industry 3.0. Once they had all this assembly lines manufacturing in bulk, then they discovered, why don't we just automate a couple of processes instead of having humans do things? So that's where automation, computers, and electronics came in, where robots were used to manufacture the parts that not only reduce the cost and improve the delivery time, but it also improved the quality of the goods that were manufactured. So time to put it into market was much faster than any other product that was done before that. And 40 years down the road, we are looking at Industry 4.0. So we took all this information from 1, 2, and 3, and we wanted to connect all this different aspects of manufacturing and put together into a virtual space using computers, using Internet of Things, and using our internet technology networks. So today we can basically connect to different systems, from machines to different plants, and we can actually visualize that from a remote location. So we don't have to go travel to different facilities to diagnose a problem. We can do all those remotely. And this has further reduce the cost of a lot of products that we are manufacturing today, and getting real-time updates. One of those examples that we see is shipping. So when we order something off Amazon, we know when the product gets picked up, scanned, and UPS picking it up and going to the sorting facility and getting to the local destination. When it is being delivered, we get a notification. So all this is happening due to this revolution of Industry 4.0. So what exactly is Industry 4.0? We've been hearing this for almost a decade. The main aspect of, with respect to Industry 4.0, with respect to manufacturing, is focused mostly on interconnectivity, automation, machine learning, and real-time data. So, for example, you have a manufacturing facility and you want to know how your robots are working in real time. You can actually connect to those sensors, do some analytics, and you can know the health in real time. If you're running a power grid, so you can see what the wind speeds are and optimize it so that you actually are producing more wind energy in real time. And you can connect to different supply chains and see how they have been working in real time and provide the strongest resilience. One of the good examples for that is, during COVID-19, all of a sudden, a lot of these automotive companies and different manufacturing industries shut down immediately without, hesitating, for the safety of the associates. And when they were brought back online to manufacture products, each company has hundreds of supply chains, but there was only a little bit of effect on those supply chains when they started running back up. So that means that they actually had a strong resilience approach due to this IoT technologies, working with their customers and the suppliers and bringing everything together with minimal impact. Some of the industry trends, especially in manufacturing for Industry 4.0, has been with machine programming and machine connectivity in operations. That has become one of the biggest challenge today, because a lot of manufacturers still use legacy systems that runs on Windows NT and Windows 98, and you need to have some sort of a really highly skilled programming language knowledge to get those machines connected and hooked onto the network without affecting the process capabilities of those machines. So that's one of the trends these days. The second thing is database management and application integration. So once we start collecting data from all those machines from hundreds of facilities, we need a strong way to have proper load balancing, right architecture for data storage, and how do we integrate all this data into some sort of an application where users can use it. So that's been one of the biggest trends. The second thing is, as we start going into future of manufacturing, we don't want to have to do everything manually. Everything needs to be somehow assisted by an intelligent service through, for example, human machine interface, augmented reality, wearable technologies. If you have some sort of machines that are thousands of miles away, you can use augmented reality and wearable technology to diagnose those machines remotely and bring them up online with minimal impact to production. And along with that, we're also adding so much of these edge devices around this manufacturing floor. And at some point, we need to have a strong manufacturing security policy for all these edge devices. And that's been one of the biggest areas a lot of companies have been focusing today. And apart from that, there are other areas as well, like additive manufacturing, where they're actually using data science techniques to learn from different designs that they have manufactured before and try to optimize for better performance, and using additive manufacturing technology to build those more efficiently, using simulations and using cloud technologies to basically improve the process and improve the efficiency in manufacturing. So with that said, manufacturing is a very, very wide field, and data science is pretty new, but especially for manufacturing, because it's an irony that manufacturing always use data to solve specific problems, but they never thought about using that to solve potential problems or how it's affecting some other underlying issues for a subsequent process. So that's been very intriguing for me, and that's where manufacturing companies have started to realize and start harvesting data to solve potential problems even before it actually occurs. And why is this drive for using data science in manufacturing? The biggest driver is the customer. The customer wants the products at the right time, at the right quantity, and at the right cost. So if you order something online, you don't want to overpay it, but you still want that to be delivered immediately as soon as possible. And you want it to have the best quality as well. So it's all customer needs. That's what it's actually driving this entire process of data science, implementing data science in manufacturing. And this concept is not new. It's been there for the last 50 years. And the first of such system was developed was right after Henry Ford's assembly lines. Toyota, they wanted to figure out why their products were very inferior compared to their counterparts, what they were manufactured in North America. And when Taiichi Ohno, he came to US and he saw how organized the manufacturing processes were, he learned a lot of those things and went back to Japan, and he saw some of his products that were manufactured. All the good parts and bad parts are always put together. They were never separated out. They were never highlighted, saying that don't pick up these parts and pick up only good parts. So it's all mixed together. So that eventually led to producing inferior products. If you remember early days of Toyota, one of their cars and their products they manufactured were really inferior, and that was not even comparable to what they actually produce today. So based on all this knowledge, Taiichi Ohno, he decided to build a system to produce the best products out there to their customers. And it was all based on Toyota philosophy. So the image on the right actually shows that production system. So main two pillars of his production system was just in time. So basically producing the right products, right quantities in the right time. That needs to be one of the utmost strong pillars for producing any product. And the second thing was Jidoka. Jidoka means small automation. as you have more and more humans on the production line, it becomes a very repetitive process, and it affects the efficiency as well as quality of the product. So that's why he made small automations as one of the pillars for producing the highest quality products, and along with that, continuous improvement. So once you produce a product, it's never the best product, so you need to go over in a cycle to refine it, to make the best products out there. And one of the outcomes of that is Toyota Corolla. They've been making it since 1970s. They've mastered the product, and they've sold millions of those cars to date, and it's still one of the best-selling cars out there. And the strong pillars actually leads to high customer satisfaction, highest safety, highest morale, and satisfying the customers. So with these drivers, we did a lot for like last 50 years, but at some point we reach to a point where we can only do so much with traditional methods, and that's where data science actually comes in. Data science helps in automating some of these aspects, solving problems that we couldn't see before through deeper insights, and then we can use machine learning techniques to automate some of these processes that were done manually. And when it comes to data science in manufacturing, before we get into a little bit of about different applications in manufacturing, I wanted to give what is the skill set for a data scientist in manufacturing. It's always known that you need to have domain knowledge, mathematics, computer science, that forms data science. But in manufacturing, we just replace domain knowledge with manufacturing expertise. And that manufacturing expertise encapsulates three different things. One, you need to understand the business, how the business works. Second is engineering. So you need to know how the products are designed, how the logistics work, what is the quality aspects of the product, what is the safety parameters. And next is production. So you need to see how the assembly lines work and how we interact with machines in manufacturing the best products out there. So that eventually encapsulates the manufacturing expertise. So that is very, very much required in becoming a manufacturing data scientist. Without these expert skills, it's not just with manufacturing, but it can be for any other domain. Without really good domain expertise, will never succeed in data science. So that's why it's very, very important for knowing this domain, having this domain experience. Some of the tools that manufacturing data science teams actually use are different programming languages. We're not sticking to R or Python. There is different programming languages, different data platforms, Hadoop, Spark, SQL Server, Postgres, deep learning tools, ML and AI different tools like TensorFlow, Keras, XGBoost, visualization tools. We have Tableau, Power BI, and so on. Ingestion tools and development tools, RStudio, Jupyter, Visual Studio, VS Code, and so on. So there is no standard set of tools. It always depends from project to project. You need to have like a Lego block architecture, so you can pick and choose to provide the best solution out there. So once we know what we expect from a manufacturing data scientist to the tools they use, the next is going to be what problems are we going to solve with these tools and with this knowledge. And actually, there's no limit on number of problems that we solve. One of the biggest problems that are out there in manufacturing is machine downtime. We want to avoid machine downtime at any cost, because if the machine is down, we're not making parts. If we are not making parts, we're not making money. If we are not making money, then we're shutting down the entire supply chain. So that's why maintenance is one of the biggest areas and one of the most immature areas in manufacturing. Next is process monitoring. We always need to monitor our process to make sure they're producing very high quality products with small deviations and take preemptive actions to avoid any deviations, big deviations. Next is predicting quality. So once we monitor the product, we already know how the product quality is going to trend over time. So once we can forecast it, we can eliminate any sort of quality anomalies in the future. Next is AI image analytics. After predictive maintenance, the second thing today manufacturing industries that spend a lot of money is on people doing manual inspections of the product. They look for conformance, for scratches, scuff marks, any sort of physical damages. So if once you take an entire manufacturing facility into account, you actually have hundreds of inspectors doing the same repeatable job. And today, the biggest trend is to use AI technologies and AI technology and vision inspection to take it a step further, to do quality inspection as well as doing traceability. If a part actually goes out, a non-conformance part goes out of the manufacturing floor, then we can actually trace it back with all the images and why an AI said it was a good part or a bad part. So I can actually do the entire traceability within a fraction of minutes, which was pretty much impossible back in the day. So this is one of the biggest areas. Next is environmental monitoring. So we want to start monitoring how the environment actually affects different manufacturing processes, using NLP to solve problems like reading up machine repair logs, to improving the safety of the associates. Next is one of the biggest applications is human body motion analytics, where you can actually monitor how a person assembles the part and assess what are the potential safety issues. Are there any RSI issues? Is the person good enough to is physics good enough to work in a particular station, or is it actually affecting a person's health? The other application is KPI forecasting, where you need to forecast KPIs 6 months, 7 months down the road using time series forecasting techniques. Product quote pricing. So you can, if you're making a highly customizable product, then you can actually use all the data that you have collected for tens of years to build a prediction model to predict those product quoting. Weather forecasting, supply chain and bottleneck analysis, and so on. And there are so many applications today, and some of them we still haven't even discovered. So there is quite a lot of applications that needs to be discovered and to solve a lot of manufacturing problems.
Hey, Nagdev, for those of us who aren't as familiar with manufacturing as you are, what does KPI mean and what is KPI forecasting?
So KPI is called as key performance index. So we want to measure an assembly line's performance. So if they were targeted to produce 1,000 parts a day, if they produce 1,000 parts, it means that they're working at 100% efficiency or 100% target. If they do produce 900 parts, it means that they're working at 90% efficiency. So we want to make sure that we produce all those parts what was the target parts, and we want to make sure that they produce the same quantities. If there's any sort of anomalies that are happening in the future, we need to know ahead of time. If our KPI, our key performance index, is going to start dropping in 6 months, we want to know that ahead of time. So we can use our historical data to predict what's actually going to happen in the future. So that's just one of the examples for a KPI that can be even attributed to how humans associates are working, or how machines are working, or how safety related issues. KPI is just an acronym that can be used for different measurement factors. Hope that answered your question.
Yeah, thank you. Thanks a lot.
So manufacturing data. So manufacturing data, we collect data from different processes. One can be from machines, one can be humans, one can be from product, but purchase orders, environmental measurements, different IoT sensors, badge in, badge out information. So there's so much of data within a manufacturing plant, and a machine can, automotive plant can generate almost close to 100 terabytes of data each day with all the machines connected through an IoT infrastructure. So that's a lot of data. And data can, like I said, it can be anything. It can be images, video, sound, sensor data, process data. And so once we collect all this data, we're not going to store all this data because it's a lot, and we probably are going to take over an entire cloud infrastructure just by storing all this data. So we try to figure out what is really needed for the future and what is not. For example, if you want to store images of the products that we did for inspection, so we kind of store those images. Sensor data, we want to aggregate all the sensor data into say by day or by hour and just store that aggregated data. And if you're collecting any process data, again, we're taking all the samples, aggregating it into one observation and just save the data. So that's one of the ways we can handle that huge amount of manufacturing data. So like I said, one of the biggest factors for manufacturing cost is maintenance. Maintenance, it's been, there are different techniques for maintenance that has been there for a while, but predictive maintenance has taken a step further in improving the efficiency of manufacturing process. So predictive maintenance, we kind of hear it here and there from articles about data science that's being published, but it's been there for quite some time, since 1990s. If you just go to Google Scholars and type in predictive maintenance, you'll find at least 2 million articles, books, and research papers published about it. But it's all been done in an experimental setting. All these research papers published are based on an experimental setting, but it only took to the next level by implementing in an actual manufacturing facility because of the recent trends that happened in like last 10, 15 years. One of the things is, like I said earlier, connecting legacy machines to the network to collect all the data is hard because some of these machines are 20, 30-year-old machines where the companies that manufactured those machines don't even exist. So the drivers and software support is absolutely nil. And that's where the trend actually changed to this wireless sensors. So instead of connecting these machines to the network, you rather use this wireless monitoring sensors to these machines to collect data like vibration, current, voltage, pressure, temperature, and so on. There are companies that make an array of 50, 60 different types of sensors, which you can actually use on any sort of machines and try to reduce that development time. Like I said, again, deployment is hard because most of the research was done based on experimental data. It wasn't based on real world data. And we've started seeing a trend in manufacturing where these companies who manufacture the machines have started to implement these sensors within the machines and providing the entire IoT connectivity to the machine. So as soon as you plug in the machine, set up the machine on your manufacturing floor, you're collecting data from day one. So you can do analytics in real time, and you can actually implement your ML models right on the machine. So it can keep monitoring its components. The machines can keep monitoring its components and use your own ML models to do any alerting and let the maintenance know about any sort of potential failures. So that's been the recent trend. So we talked about predictive maintenance, why it's really important for manufacturing. The biggest cost for manufacturing is machine downtime. If we look at machine downtime on an average in 2014, we saw the downtime cost was about $164,000. And by 26, it exploded to $260,000 per hour. So that's a lot of money. In automotive industry, 1 minute of downtime can cost upwards of $22,000 to about $1.3 million an hour. So there is no room for unplanned downtime. We want the machines to keep running and at the highest efficiency as possible. And in some automotive companies, it was estimated close to $50,000 per minute, because all these machines are, all these automotive plants, they run in assembly line. If one machine goes down, the entire assembly line goes down. So you have hundreds of people working on that assembly line, standing still until the machine gets fixed. So it not only affects the manufacturing plant, it also affects the entire supply chain. So we don't want any sort of unplanned downtime happening. So that's where predictive maintenance comes into picture. So the whole concept of predictive maintenance is we want to predict if the machine's going to go or machine's going to fail in the future. So once we know if the machine's going to fail in the future, we can do a couple of things. We can increase the tool life. So if we know the machine's going to fail today, or if it's going to fail in next 1 week, we can actually run the machine for until the last day and use up the entire tool life of the machine before we actually retool the machine. We can also improve the products. If the machine's actually failing, then it directly correlates to the product quality. So we can improve the quality by doing the maintenance at the right time. And it does not affect our supply chain, so we're not losing any money because of unplanned machine downtime. And we can also predict the process. So once we know how our machines are working, it kind of ties along with how the machines are going to work, how it actually works in the future as well. This is just an overview. The image on the right is an overview of how predictive maintenance works. So we actually have time on the x-axis and signal on the y-axis. Signal can be anything, vibration, temperature. Once we start doing signal processing, it means that we're just collecting raw data and doing some kind of trend analysis and say that, all right, if the trend is increasing, it means that it's anomaly detection. If we just do that with an Excel spreadsheet, we can get an ROI of 1 to 3 times of the investment. Next is fault diagnosis. So if we can tell, all right, there's something going wrong and the fault is going to be, the gear is going bad, so we probably have to change those gears. So the ROI we can expect is 3 to 5 times. But if you can tell when the machine's actually going to go to a complete failure, for example, the machine's going to fail in exactly 22 hours, then we can expect an ROI of 10 to 15 times. So in that case, we're actually monetizing the project within the first 3 weeks of implementing a predictive maintenance strategy. So the next couple of slides, I want to go over signal processing, anomaly detection, fault diagnosis, and remaining useful life prediction. So first, we need to collect the data. So there are hundreds of sensors that are out there. The most common sensors are vibration, temperature, current, and pressure sensors. And you can either connect it through PLCs or use IoT technologies to actually connect those sensors straight to the cloud. And next is signal processing. So once we collect those data from the sensors usually collect at a sample frequency. So if you say you're collecting at 100 hertz, it means that for every second you're collecting 100 data points from that sensor. The range for sensor data collection ranges between 100 to 44 kilohertz. 44 kilohertz is the audible sound. 100 is usually for current and voltage, but I've seen sensors going all the way to 100,000 kilohertz. So there are a couple of use cases where you can actually go at very high sample rate, but most of the signals are usually vibration signal. You collect it for a sample at say 1,000 kilohertz, 1 kilohertz, so it's about 1,000 samples per second. And if you look at the raw vibration signal, it's hard to tell what's going on with the vibration signal. So that's why we need to do some sort of signal transformation like FFTs to tell us more information about the signal. So with the vibration signal on time series on the top and with the frequency signal at the bottom, we can tell that the machine is probably, it's mostly a frequency chart. It tells that most of the data actually lies between 40 hertz. So this is actually useful when we want to go into very in detail diagnosis. So once we have,
there's a couple questions that are coming in via Slack, and Michael, I wonder if you want to relay those to Nagdev at this point in time.
Sure. Yeah, the first one from Julian is about changes in machinery. So if you do some kind of adjustment to a machine, maybe there's a new type of steel being used in a replacement part that improves wear resistance. How do you adapt accordingly to that sort of a change?
So once we actually do that kind of maintenance, we need to recollect the data with the new tool that's being installed. So then that's where we calibrate the model or any sort of analysis. So if we do install it, then we need to recollect the entire new set of data points.
Okay. Thank you. And then another more organizational question from Brett. What team size do you typically see for these sorts of analytics?
So it ranges. In the last company, we only had 2 people. In the current organization I'm working, we have about 20 people with working on different projects. So it really varies from company to company and how they want to tackle problems.
Okay, thank you.
Yep. So going back to signals, like I said, we'll be at 1 kilohertz, we're collecting 1,000 samples. And that's a typical case, of course, of dimensionality. It means that using all the data to build a model is not feasible. So that's where we do a technique called as feature extraction. So here on the right, we see the signal form, and we have time series at 0 seconds, 2 seconds, 4 seconds, 6 seconds, 8 seconds, 10 seconds. So what we do is, instead of taking all the data to build a model, we take a snapshot of that window, say 0 to 2 seconds. And we take the data and we do a thing called as feature extraction. So there are different types of feature extraction. The main classification is statistical features. So like, what is the max of the signal? What is the min of the signal? What is the mean, standard deviation, kurtosis, skewness? So you can actually extract all that information. And if you want to go into a little bit of domain features like peak velocity, peak acceleration, RMS speed, you can do that as well. And in a lot of cases, we end up actually using a combination of both to provide more accurate models. So with this, instead of having 1,000 samples, now we actually have a snapshot of the entire 1 second into about 50 different variables that actually represents your entire data set. So that really helps. And we do this not only with time series signal, but we also do with the frequency transform signal. So you end up having like 100 observations instead of 1,000 observations. So you're basically reducing that curse of dimensionality. If you ever want to do that, I actually have a package called Ensemble ML, where you can actually do feature extraction and signal transformation in just one line of code. You can install it using the GitHub link and read the data like a CSV data file, and you can do feature creation TS data, and it creates your list of features in time series. And if you want to do frequency transformation and extract features, you can do that using fast Fourier transforms with this function and data, and it extracts everything. So it's a very straightforward package, because I spent a lot of time for every project trying to create these features. I ended up building a package that actually automates this entire process. And next is fault detection. So fault detection is, the goal is to detect the faults as early as possible. And sometimes it's also referred to as anomaly detection in different domains like finance or in healthcare and so on. For anomaly detection, there are mainly 2 types of techniques: supervised and unsupervised technique. In supervised technique, the concept is you take a machine that's running in healthy condition, take the data, use that as calibration data, build a model, and anything that actually goes over the limit is going to be an anomaly. So that's the simplest way. In supervised learning, you take both healthy data, unhealthy data, different fault conditions, build a model, do a 2-class classification model, and use that for predicting any anomalies. These are some of the models on the right side table for unsupervised and supervised learning techniques. And if you want to test out any of these algorithms, feel free to get to my GitHub link. And I've actually given tutorials on how to implement each of these models for both supervised and unsupervised learning. The chart on the above is actually based off of autoencoders. I like to use autoencoders for fault detection, because it not only works with signal data, but you can also use image data to do fault detection. So it's very, very nice, handy tool. This is how you do it. This is how I actually personally do it for using autoencoders. We basically split the data into train data, test data, and initialize a H2O cluster. H2O is a package that is very nice deep learning package. Then you convert into H2O objects for training test data set, build a deep learning model, and then you can actually find out what the anomaly score for the trained model is. And then you can set anomaly limit for the data that you're trained on. And basically calculate the scores for the test data set. So you take the trained data set, find the anomalies, set the limit where you want the anomaly threshold should be. You take the test data set and see how the anomaly actually works or differs. This is my GitHub link. I actually have the entire presentation notebook style report on how to implement this along with the data set. So you can definitely go check it out. Fault classification is a typical classification problem. If you are aware of how classification works, so you basically have different class data, for example, bearing issues or electrical issues, motor issues. So you take all this data, label data, and fit it into a classification model for supervised learning, and you end up getting an accuracy score, and you can use that to do inference on. And in unsupervised learning, you basically use sum of square or total sum of square technique to identify number of clusters, and then identify the faults using clustering techniques like k-means, hierarchical clustering, SOM, and so on. Supervised clustering usually tends to provide higher accuracy because it's actually training on the labels. So if you have the label data, go for supervised learning. If you don't have label data, then you can go with the unsupervised learning.
Nagdev,
yes.
As a time check, we have 10 minutes left in the session, and there is, I think, one question on the Slack channel. Michael, would you like to introduce that?
Sure. Andrew asked, is it feasible to do feature extraction in real time, and would that be helpful?
Yes, you can actually do feature extraction in real time. If your problem actually requires low latency, then you need to do it in real time. But if it doesn't require, then you can actually trunk it into small samples and do it. It's all a latency issue.
Great. And I'll jump in with one of my own questions, not on Slack, but just for myself. For the fault classification here, do you tend to work closely with the engineers, the manufacturing engineers, to kind of understand the functionality of the devices, and what type of signal might be correlated with what type of fault as you do this as well?
Yes, so that's going to be the key point when we actually install the sensors and collect the data. So we need to get that subject matter expertise. So yeah, to your point, yes, we need to work with them to figure out what sensors and where we need to install them. So moving on, fault classification, simple classification problem. Split the data into train and test set. This is using a carrot package. So we set up some of the process parameter tuning parameters here. We trained a good random forest model, and then we can use the test data to predict on the model and see the confusion matrix, how our model has been trained. It's a simple classification problem. There is nothing really crazy about fault classification. Next is the last part of predictive maintenance is remaining useful life prediction. So this is where the biggest ROI is. So the goal is, if our machining is running in a current state, so how long does it take to go to a complete failure? And if we know that it's actually going to fail in, say, 9.5 days, so then we can actually plan the maintenance accordingly to fix that issue. To do this technique, the data that we use here is anomaly scores. So for example, in earlier slide, I showed this anomaly scores using autoencoders. So one of the other advantages of using this autoencoders is it provides this anomaly score, and we can use this to fit a curve, to do curve fitting. So if this was the point where the machine failed, we could actually use a curve fit to actually predict when the machine's actually going to fail. So using either linear trend line to forecast when the machine's going to fail, that actually creates a lot of error, but exponential is usually the preferred way because it's a very accurate way of predicting when the machine's going to fail. And the other ways that you could do is using time series models like ARIMA or LSTM in neural networks. So other thing is you can make this into like a regression problem. So you can take all this data and try to take a step back and say, at this point, the machine's going to fail at 9.5 days. So your prediction variable, response variable is going to be 9.5, and this is going to be 8.5, 7.5, 6.5, and finally 0. So you actually build it all the way from bottom-up approach and use all your feature data to make it into a regression problem. And that is the highest accuracy you could ever get with remaining useful life prediction model. So like I said, it's this remaining useful life actually provides the highest ROI or monetization for your company, and this is where the golden egg for predictive maintenance is.
Hey, Nagdev, I have a quick question for you.
Yes.
So a lot of these robots and the mechanizations, heavy equipment, they're being built by manufacturers and then installed in these warehouses. And they're being installed in many warehouses. Is there some sort of a data repository that's there by year for those particular make and models, which is more of a bigger data set, which can benefit all of the potential customers who are using those products? Because the more data you have, the better you can, as far especially for the remaining life expectancy, or even anticipating if there is a particular fault, which could be a particular lot of those manufactured equipment as well.
I'm not really aware of any such repositories, but I think that's a very good point, that we do need such repositories to really help, accelerate this process.
Okay, thank you.
Yeah. Thanks for that question. So all the things that I've actually explained here are based on my GitHub. So if you want to go execute things, I actually have a binder link. So just click on this icon on my GitHub, and it takes you to RStudio or Jupyter, and you can actually run all my code and with all the data sets. So if you have any questions, just let me know. I could help you out with running this interactive session. And it's actually free to run, so you don't have to create any logins. So it's immediate to set up an environment and run those code. So deployment, so once we have all this information, one way we can put together is, we need to put it into an inference script. So one is collecting new data, collecting new features, converting everything to features, doing some anomaly detection function, putting into a fault classification function where you actually load the data, score the data, and return the results. So you want to put everything, all these concepts, into like a function-based script. And finally, once you have it, all you need to do is call these functions. And for example, this is the process I usually follow. Collect the data and do anomaly detection. And if there is an anomaly, then do fault class detection and do remaining useful life prediction. So if there's no anomaly, then there's no point in actually running other two functions, right? So, and take all this information, either push it to a database or push it to an application. And you can run this entire script either as a cron job or an API. It depends upon how you want to deploy it. And the last part is, you want to containerize all this projects. So we want to put into like an isolated space to run this in always a stateful manner. So that's why Docker containers are pretty much kind of a standard for deploying a lot of data science applications. Typical Docker container script looks like this. So you pull an image, you install any sort of dependencies, install any R packages, and you copy the script into the container, and you call a command script saying that, hey, run this inference.r script. So it basically runs, does its action. If it's a cron job, so you can actually run it once every 5 minutes, 10 minutes, or every minute, returns the result wherever you want to send it to, and shuts down. So it's always going to run without any sort of hesitation, or it doesn't really matter what you do to your host machine. And the last part of this presentation is going to be, how do we put this into an architecture and deploy it? In my experience, what we do is we want to put all the source code, documentation, notebooks, and CI/CDs into your Git repository. And you want to have a container registry where you can actually store all your Docker images. If you want to do any quick testing, you can use Google's Cloud Run. Very simple to do. and you want to have some sort of dev environments using either AI platform or a compute engine, and you want to store all the data into a database. And Kubernetes on GCP actually takes on most of your work and does everything in a very simple, straightforward manner. So it lets you focus more on building pipelines rather than actually setting up infrastructure. So it's all GCP does a very good job in taking most of the work. And this is how a typical architecture looks like. So if you end up doing a cloud-based architecture, if you are very focused on latency related issue, then you want to do it on your machine. So you want to deploy these models on your machine. If latency is not an issue, if you're doing something, it breaks with a high notification time period, then you can actually do most of this in the cloud. It's faster, it's easy to develop, and it's very inexpensive to use. So the steps involved in pipeline are data processing. You want to train models, containerize the models. You want to build some CI/CD pipelines and deploy it in a Kubernetes architecture.
Nagdev, we're great. You're right on time. If you can wrap it up,
Yes.
we'll bring this to a close.
Yes. So my final comments are, big data analytics in manufacturing is growing, and it's going to keep growing. The smart manufacturing solutions are growing. New companies are popping up every day. And predictive maintenance is a very mature area, so there is a significant ROI for manufacturing companies. There's a lot of solutions that are mature solutions that are out there to implement it and see the value immediately. My last comment is, whatever you do, standardize and automate your deployments so it's easy to scale the solutions. And that's the end of my presentation. Feel free to reach out to me on Slack. I'll be there to answer any of your questions. Yeah, if any questions are there, let me know.
Great. Nagdev, thank you so much for that both detailed and conceptually descriptive talk. I appreciate that you put the code and the links to your GitHub repository and all the solution details that you described in your talk. The slides, if you could make your slides available by sending them to Thomas Geib, who is doing our AV, we'll make sure those get posted for the audience members. Finally, Nagdev, I think you're a great example of the value of cross-domain knowledge. So it's really this combination of business knowledge, engineering knowledge, data science knowledge, putting those all together in ways that can produce the kind of solutions that you just described. I want to quickly thank Thomas for doing our AV, Tuhin and Michael, Tuhin Mitra and Michael Bloom for moderating. And I want to thank once again the WMR users group, represented by Paul Egler. If you have questions about the WMR users group and other applications of R, please reach out to Paul Egler via Slack, and I'm sure you'll have a great conversation. Thank you for attending. The remaining questions, if there are any, I would ask Nagdev to follow up on Slack and answer those personally, and you can all tune in at your convenience and see that continuing conversation. We hope to see you on Thursday. And Nagdev, once again, thank you very much. And thanks to all who have listened in.